Kia ora tātou. I want to go back and have a look at why we're learning what we're learning. It's not just about passing a course, it's about some really important understandings that you need to take away from this course, more than just the actual things that you can do from the course. So first of all, it's about developing a viable mental model of a microcontroller-based embedded system, so that when you look at a problem, you can start to imagine what the software and hardware will need to do to actually make it work for the particular environment that something is working in. And you can see what's going to happen in your mind as you start to design it. That's one of the big goals of really this part of the course. And how we do that is you need to be able to understand how to make a microcontroller-based embedded system reactive and responsive to the environment, to the things that are going on around it. Of course, if things in the environment are going slower or faster than the microcontroller, then you need to be able to control the microcontroller's speed of operations to match that, so that things are going to happen when they need to happen and not before or after. Part of this understanding, of course, is the fact that this machine is going to have to operate without human intervention. It's an automaton. And in many cases, humans have little to do with the embedded systems that are going on, whether it's a sprinkler system on a farm, or whether it is your refrigerator, or whether it's your oven, or whether it is your fuel control unit in your car. Of course, part of this, and we're going to look at this in more depth now, is how to make hardware and software work together. And there's some really important concepts going to come out in this. So let's launch into this. We're going to go down to section 2.7. That's timers and counters. So that's on page 129. And of course, the main goal here is this reactive and responsive nature. A microcontroller's ability to react with the real world is limited by its sequential nature. Of course, if you're looking at an FPGA, you can design things that are going to happen in parallel, because that's how you can configure the FPGA digital circuits to work. But in a microcontroller, you're limited by the software, which is going to process operations one after the other in the sequential nature. And that means it's impossible to predict how long things are going to take. If things are, you've got if loops and other things happening inside your software, you cannot create something that's going to happen on a regular pattern. And to give that facility to embedded systems engineers, microcontroller manufacturers provide a number of hardware timers or counters, which are pretty standard inside almost all microcontrollers nowadays. And these allow you to do things. They allow you to control an output or check an input on a really defined, fixed and exact timing schedule. So it allows you to do both inputs and outputs with complete, really good accuracy, okay? As accurate as the crystal is on your microcontroller generally. For instance, take a petrol engine. What happens there is the cylinder, inside the cylinder, the piston goes up and down, and on every fourth cycle, fuel is let into the cylinder, and it must be ignited by a spark for it to explode and to force the piston to go back down again. The timing of that is essential to get right. If you don't get it, if you get it too early, then the explosion happens before the piston gets to the top of the cylinder, and that will really reduce your compression. Now, and then if it happens after the piston has got to the top of the cylinder or at the top of the cylinder, then it's a bit late actually. So you want the spark to happen so that the fuel has got time to ignite, and just get it as the piston is about to go back down again. You want that massive amount of explosive power to happen right critically then. And this happens in your a car which is revving at 10,000 RPM. You can imagine that this has to happen at very, very defined timing, perhaps down to microseconds, or even maybe even less than a microsecond accuracy. The other thing, of course, is that you want to be able to measure timing, which is completely accurate. And polling, which is where we take our inside our loop, we look at how we will check switches a number of times to see if they're needing to be actioned because someone's pressed them. Well, that sort of thing doesn't work well enough in high-speed situations. Take, for instance, ABS, anti-lock braking system on a car or a motorbike. And the whole thing about ABS is that it allows a machine to take over control of your brakes in a situation where the wheels are likely to skid. And so what it needs to do is it needs to be able to look at the speed of individual wheels and then compare them and see if one of them is going at a different rate to the others, if it's slowing down because it's starting to skid and therefore you're losing traction. And this is really critical. The amount of lives that ABS has saved is probably quite significant because it allows you to push your vehicle to, push your brakes on your vehicle pretty hard. I don't know if you've ever noticed ABS. It's you want to be really careful about testing your ABS on your brakes and do it in an environment where there's absolutely no one else around. And you get your car up to a decent speed and then put your brakes on really heavily. Practice this a couple of times if you're going to do it at slower speeds to start with, and you'll feel that the brakes shudder. And if you've ever been in an accident and hit the brakes really heavily, you'll notice that the braking of the car sort of shudders, and that's caused by the wheels reducing their speed and allowing them to be unbraked so that this stops the skidding, because you want the braking to be as hard as possible, which is just at that point where a skid is about to happen. And a controller can do this much better than a person. Again, this is an example of technology being used to allow a human to sort of back off and let technology rule our lives. Polling is not good enough for this. A lot of drivers, not a lot, but a number of drivers want to disable the ABS in their car so that they can get the cars to do things that might not normally be recommended, doing wheelies, skids and all sorts of things. And of course, people who want to drive their car, perhaps in a race type situation, wouldn't want this because they don't want the controller taking over the car. They want to control it themselves. My motorbike has got ABS, and it certainly is pretty good for braking on the straight on a road. But because it's also an off-terrain bike, you need to be able to disable it so that it doesn't, the ABS doesn't come on while you're actually riding off-road. So these sort of situations require a microcontroller to be reactive and responsive where a human can't, but also where a polling of a normal sort of inputs doesn't work well enough. So we need to be able to create some pretty cool timing. And the microcontroller has got some great features for doing that. Let's have a look at them. In the AVR, and typically most of the AVRs, you'll find that there are two 8-bit timer counters and one 16-bit timer counter. Now up here, I've made the point that we're going to use the word timer, counter, divider, prescaler. All of these things are just binary counters. So going back to your notes about what a binary counter is, okay, they're commonly clocked flip-flops, okay, in a sequence. So that's all these are, but we just call them different names depending upon how we're using them, really. That's about it. The source, have a look at this. This is from question 37. So here's a 8-bit, this here is an 8-bit counter. It's timer counter 0, TCNT 0. It has 8 outputs and it has 1 clock input. Now this will count from 0 up to 255 and then overflow back to 0 again. So this is an 8-bit counter. Now noticing that overflow back to 0 again means that the total count is 256. So from 0 to 255 and then back to 0 is 256 counts. We also have 16-bit timers in the microcontroller, and they will count from 0 to 65535 and then overflow. The source of this, in this case, I've got the 16 megahertz source connected, but there are other options. You've got things like, we can take our 16 megahertz and put it through a prescaler, which is just another divider or counter, and take one of a number of outputs and feed that into our 8-bit counter. So we've got all sorts of different things we can do. We can even take it from an external source. We can put some sort of timing source on the output of the, on a pin of the microcontroller, and that will allow us to clock from an external source rather than the internal clock. Generally, these counters count from 0 up to their limit, 255 or 65535. And then when they overflow, we can do something, and that will trigger us to do something. Really, one of the things we can do is we can directly connect the output of the timer to a hardware pin, and we can toggle this pin on and off, or we can do different things with it, set it or clear it. Another thing is that we can actually use the overflow point of the timer to call a little function called an interrupt service routine. We'll look at this in detail. Timers can be configured to start when the input clock is configured, and automatically they can re-trigger so that they'll just keep counting from 0 up to their max, and then back down to 0 and then up to their max again. When you want to stop it, typically you disable the input clock, and I'll show you how that's all done. There's another special mode for PWM for timers, which we're going to go into in one of the next lectures as well. So let's have a look at the actual microcontroller here. What we've got is, this is the MLF, or well, also the TQFP package that you'll find on the Arduino Nano or the Explain Mini or the Arduino Uno 28-pin device. And you'll notice that these pins, many of them have multiple functions. So let's just take a look. Let's see if we can find T0, which is one of the alternative functions. Okay, so it's on pin 2 here, which is port D.4. So as a normal I/O pin, port D.4 could have inputs or outputs connected to it, but it can also be configured as these other options here, but we're interested in T0, which means that this is where we would feed a clock pulse into the microcontroller to actually clock timer 0. So we can set up options to do that rather than use D.4 as an I/O pin. Output compare 0A, output compare 0B. Let's see if we can find one of these. Here we go. On port D5, you will find output compare 0B. So you'll notice that there are multiple functions of this pin. We can use it as, again, as its normal I/O pin. We can use it to as the input for timer 1, but here I'm interested in the fact that it can be an output, a hardware output, directly from timer 0. And we will find the output in 0A is here. Now, if you look at the practorials that I've done, and you'll see that, let's go down to, whoops, let's reload that. Okay, practorials, and here we go. When I've done this board, I've got a countdown timer here. These LEDs that I've put on the board, I've put on these specific pins for different reasons, B1, B2, B3. So if I go back to the data sheet, and we'll have a look at B1. Let's see, here's B1. So it's an output compare 1A. So we could use a timer to control that pin. B2 is output compare 1B. So again, we could use timer 1 to trigger that. And B3 is on output compare 2A. So we could use timer 2 to control this output. So that's why I put them on those specific pins, to show you how we can do these sorts of things. And you'll see that timer 1 has got some inputs. It's got IC pin 1, which allows you to do some really fast timing measurements. And I've used that in the practorials as well for a specific reason. And so if I go to front page practorials, and we'll have a look at timer driven ADC, where, no, I haven't put it on that one. Let's go to the next one. Oh, this, yeah, sorry, it is. The opto pin here is on B0. So this opto sensor, this infrared sensor, I've put that on B0. So if I had a look at B0 on here, B0 is the ICP1 pin. So that's input compare pin. So you can see these in the demo board that I put together. I've done this for specific reasons. Then we've got timer 2. Now timer oscillator 1 and timer oscillator 2. Now it's really interesting in this, in the Arduino Nano and the Explained mini board and the Arduino Uno boards, this is where your 16 megahertz crystal is connected to, Xtal1 and Xtal2. So you can't use B6 and B7 as normal I/O pins because they're configured for that. In some of the larger AVR microcontrollers, they separate these out. And the crystal would be on perhaps its own pins. But then these two other pins, TOS1 and TOS2, timer oscillator inputs. Now these can be used to connect a little tiny timing crystal to, for instance, a 32.768 kilohertz crystal, which allows you to do, if you think about it, 32768, that sounds like one of 2 to the power of something numbers, and it is. And so if you divide it down, you can actually get 1 second timing interrupts. And this is what you might use if you were going to connect to design a little clock. So you'd have a little 1 second timing event coming off this crystal here. So let's go down and now have a look at an example of using the timer. So let's have a think about it. How to accurately control the timing of an external device without involving counting in the program's main loop. This is how we're going to get away from putting if statements and waits and delays in the main loop. We're just going to set up a timer to do something for us. And so what we're going to do is we're going to use timer counter 1, which is a 16-bit timer. So let's have a look at the data sheet. So on the data sheet, I'll just open that up. We've got on the left here, we've got section 15, 16, 17. So 16 is timer 1. So timer 1 has got, here's a bit of a block diagram of it, but basically we're interested in this particular register here. This is timer counter 1. And so it is a 16-bit register. So it counts from 0 up to 65535, and then it will overflow. And with all sorts of control logic coming into it. The signal for the clock will come in from here. We decide, are we going to use the prescaler input? Are we going to use the external pin input to the control logic? And that goes into the counter here to do the counting. We'll look at some of the other features of this as we go through different demos. Right, so first of all, in this most simplest basic operation, we want it to count from 0 to 65535, overflow back to 0 again, and keep counting. So we're going to set this timer up to do this. Now what that means is, how long will this take? Okay, so that depends on the crystal frequency, and we're using 16 megahertz in our micro controller. So all these micros are all set up exactly the same, different board layouts, but they're pretty much set up exactly the same otherwise. So 16 megahertz, that means that one count takes 62.5 nanoseconds, or 0.065 microseconds, or 0.000065 milliseconds, or this many seconds, okay? So that's one count at 16 megahertz. So if we put one count into our 16-bit timer, and what I've got here is I've gone into the simulator and I've created a timer, a 16-bit timer. And what I've got is I've got my 16 megahertz coming in. We'll just ignore this bit here for the moment. And it's coming in and it is clocking my microcontroller, sorry, my timer at one count every 62.5 nanoseconds. So how long would it take for this to count from 0 to 65535 and overflow again back to 0? So that's counting from 0 to 0. Let's have a look at that. So in this situation, I've got this clock coming in and it's going to my 16-bit. So I've got no prescaler. We'll come to that in a second. We've got 16 megahertz coming in. It is counting at a rate of 62.5 nanoseconds per clock, or each clock takes 62.5 nanoseconds. So that means a count of 65536 takes 4 milliseconds. So every 4 milliseconds, we can do something on a specific timing schedule. Now that's not always useful. For instance, 4 milliseconds, yeah, sometimes you want things to happen at different timing rates. It might be longer or shorter or something. So let's take the example, first of all, that we want to insert a robotic assembly line wants to insert a component every 200 milliseconds. So we need an accurate 200 millisecond timing amount. So what we're going to do is we've got another timer here, the prescaler, and it's got some pre-configured inputs or outputs, sorry. We can take the clock in, and instead of skipping it straight round to the 16-bit timer, we can pull it in through the 8-bit timer. Now what that means is this would go from being a 16-bit counter to a 19-bit counter. And then of course we could use the 64-bit one out, which means that then we wouldn't have a 16-bit counter or a 19-bit, but we would have a 22-bit counter. And we can go all the way up to 1024. So we've got a 10 bits here, 16 bits here, which gives us a 26-bit counter. Now what that means is that our code can then, instead of our counter here being fed, I'll just bring this down so we can see it down here in a bit of a clear way. So instead of this counter being fed with 16 megahertz clock, we've divided it down to 15.625 kilohertz. We've put it through the 10-bit prescaler, so it's 15.625 kilohertz, which means that this is now getting a clock pulse every 64 microseconds. So of course, to count from 0 to 65,535 and overflow back to 0 again will take 4 seconds. So that's pretty cool. This is how we get a 4-second interrupt or something like that. Of course, if we're looking for something, now at this stage, we're looking for a count of about 1 second. So if we take our counter and we use the divide by 26 here option, then what we get is a 62.5 kilohertz clock, which means that we're getting a pulse into our 16-bit counter every 16 microseconds. So again, 16 microseconds times 65,536 gives us a timing period of 1.048576 seconds. So we've got about a 1 second timer, which is what we're looking for. So we want to set up our timer so that it gets, it takes the 16 megahertz clock into the prescaler, gives us a 256, and then that is going to our 16-bit timer, and then, excuse me, and then on overflow, we want to cause it to give us an interrupt. So let's have a look at that code. This is the code that will make it all work. Here we go. So this is the about 1 second timer, 1.04 seconds it is roughly. Now this would make a really good heartbeat LED in a piece of equipment. It's really disconcerting for humans to look at a piece of equipment that has got no LEDs on it and think, is it working? It's really hard to tell. Whereas you can fool humans really nicely by putting a big box on the wall and saying, you know, critical device, and put nothing inside it but a flashing LED, and they'll be perfectly happy that everything is fine. But take away the LED, they'll be really worried about it, okay? So a heartbeat LED, just to say that the device is working, is really very nice for humans to look at. So that's what we're creating, a little flash about every 1 second. So how are we going to do that? Well, first of all, as I've said, we need to configure our timer. And this is the code that we'll use to configure our timer. Let's go to the data sheet and have a look at this. So in the data sheet, what we've got is we've got these registers. And these are how we control everything in the microcontroller. So we've got timer counter compare register A. So this has got all these options here. We're not going to look at this one yet because we're going to use it in its default mode, which is where these are set to 0 at power up, and we're just going to use that mode. We're going to go down to timer counter compare register 1B, and we're going to look at some of these pins. So again, what we're really interested in is these, the clock source pins. If you have a look down here, the 3 clock select pins, but select the clock source to be used in the timer counter. So what I've said to you is that we can use the 16 megahertz, we can use an external pin, we can use the prescaler. So let's just go down a little bit further and we'll see what the different options are. So here we go, we can have no clock source. So this is how we turn a timer off. We set these 3 bits to 0. If we want no prescaling, we must set this bit to 1. If we want to divide by 8, we do this. What we're looking for is this line here, which is the 256 division. So we need to set this bit to 1. But just have a look to see how you might use it to get it to take an input from an external pin T1, which is a specific pin, okay, on the microcontroller, and whether we would clock it on a positive or a trailing edge. So we could have an external clock source coming in, and this is how you would set it up. So in any data sheet from any microcontroller, you want to start looking for these sort of features. How do we control the clock source, and what are the different options? So we're looking at setting CS clock source for timer 1, bit 2 to 1, okay, and we'll leave these at 0. So let's go back to our code and just see if we've got that. So there it is there. That's the first bit of setting it. So what that does is gives us a prescale of 256. Now, you'll notice that I have not cleared bits clock source, timer 1, bit 1, and bit 0. The other 2 bits I've left and I haven't bothered to look at. And there's a reason for that. The manufacturer says to us that when the device is powered up, all of the sequential logic in the microcontroller is reset. You'll notice Kevin talked about reset circuits in the first part of the course. And so all of your microcontroller is reset and all your registers are cleared to 0. Okay, so this is really important to know this. So if we're going to stick a piece of code in this part of the of our software, which means it's called once before we go into the automatic or automaton type while loop, then we can just configure this without worrying about bits 1 and bit 0. But if you're going to reconfigure your timer at any time and change the prescaler, then you want to make sure that you are setting the right bits and clearing the bits you need to clear as well. That's this whole concept of state. If you don't understand that, or you need to understand that the microcontroller state it's in now is defined upon its previous state. Well, we know the previous state at power up, all the register bits are 0, and so we can just set the one we need. But later on, you might be unclear about the state of these 3 register bits, and so what you need to do is make sure you set and clear the bits you need. Okay, I'm going to go on about that sort of concept of state. So let's see, now that we've got the prescaler set at 256, what's happening is that, well, actually I can show you in the simulator because I've got this set up in the simulator. Let's go to, here's the main assignment. Now you can actually put your own stuff into the simulator. Go down here to one of these codes, blank simulator, not a question. Okay, so this is blank at the moment, so you can actually configure this. I'm going to pull into it some code I've already written, so I can import from a text file, and so here it is operating. So at the moment I've got no clock, so you can see that the counter is not working. So that's equivalent to writing all those 3 bits to 0. And if I write my particular bits clock select bit 2, then what happens is that this output of the prescaler is now fed to the input of the timer, and you can see the timer is now counting away. And you can see that the timing rate is, according to my scope, I need to just let that fully go through. Let's just get this, it takes a little while. This simulator, of course, is running in JavaScript in a browser, in a single tab in a browser. So there's some real limitations in how much you can actually do with this sort of thing. So there we go, we're sitting at 62.5 kilohertz. So that's what we calculated it to be. So our clock signals are 62.5 kilohertz at this point in time. Now, if we waited for long enough, we would find that this here will trigger. Okay, now that's going to take an awful long time in the simulator. There's not a lot you can do to sort of speed that up. You can try a bit, but it actually starts to freeze if you do that. So we'll just leave that. Okay, so what we need to do is we've got the prescaler operating now, so it's doing something, but that's only the first part of the task. What we need to do then is tell it the circuit what we want it to do when it overflows, or when something else happens. And that's what we're doing here. Timer mask for timer 1, we're setting timer overflow interrupt enable bit. Okay, so we need to say to it, I want you to give me an interrupt when the timer goes from 65,535 back to 0 again. So let's go to the data sheet again, just have a look at this. You've got to get really familiar with this data sheet, okay? So we're looking for, which register was that we were looking at? We can go back to our code and just think, okay, timer interrupt mask register. So how do you figure all this stuff out? Well, you actually just have to sit down and read a little bit of the data sheet. And this is what an engineer does, is they spend quite a bit of time. If you're working on this sort of design as an engineer, you spend a lot of time inside data sheets. So you get down here to timer interrupt mask, and here you'll find that we've got some different interrupts that we can select to happen. And this is the one we're really interested in. So that's bit 1. So here we are, bit 1, timer counter 1, sorry, this one here, bit 0, timer overflow interrupt enable 1. When this bit is written to 1 and the I flag in the status register is set, then we will get an overflow interrupt. So let's just go back and have a look at our code to see what's happening. Sorry, not there. Here, when we set this bit here, what happens is we're saying to it every time that the timer overflows, come and run an interrupt. And here's the interrupt function. Now, it's just a normal function, but it has a special name, okay? And this is how you have to set it up. It's an ISR, and this is the parameter for it, and it's timer 1 overflow vector. Now, Again, how do you know what to put into this? Okay, so it's really useful in Email Studio because you just start typing and it's got autocomplete for you and you can find the option you want. Of course, all of these are defined for you in this include file. So you can have a look in this file here and see what's going on. And you'll see all of the different interrupts that you can use. Now, we call it a vector because this is where the code vectors to when the interrupt happens. And all we've got it doing is just toggling the LED. So again, toggle LED is just a macro. You're familiar with macros now. So that macro is set up here. Toggle one LED. All it does is it toggles the bit, which means if it's 1, it goes to 0. If it's 0, going to 1. And of course, to do that, we use an exclusive OR, which is this little symbol here. Okay. So what we've got is we've got our prescaler. We've got it's counting, the timer's counting. We've enabled the overflow. Excuse me. We've enabled the overflow interrupt. We've configured the vector for it to go to. There's one more really essential line of code. And you'll notice in the data sheet, I didn't point it out, but it says here, when this bit is written to 1 and the I flag in the status register is set. So the status register is one of those really important registers of the microcontroller that just sort of underpins everything that's going on. And I can go down here to my list of registers and I'll find the status register. We'll keep scrolling down somewhere here. There we go. There's the status register. It's the I bit, which is bit 7. So we need to set that bit. This is like a global tap for all the interrupts. You might configure a dozen different interrupts in your microcontroller, but none of them will work unless this bit is set to 1. And so you can actually, at any particular point in time, you can disable interrupts very briefly to do something. If you need to, if it's sort of timing critical for some other reason, or it's really important and you don't want it to get interrupted, you can turn them all off and then turn them all back on again using this. And that's such a useful feature that in C for the microcontroller, instead of actually setting the bit ourselves, there's a little function, SEI, set interrupt. The alternative function to this to clear them is CLI, clear the interrupt flag. So now we've got all 3 things done. Really important that you know that you've got to do different things to get a timer to work. Set up the prescaler or not to take the right timing clock rate, and then you want to make sure that you've got your functions set up correctly, and then you want to enable your global interrupts. So what's going to happen now is, and this is shown in the Pactorial video as well, I've done it there, is it's just going to tick over and change our LED state from 0 to 1, 1 to 0, every second. Okay, not every half second, every second it's going to toggle it. So 1 second on, 1 second off, or approximately. It's 1.04. Remember that this is an approximate count. We'll get into those more juicy details of timers later. Now, I'm going to pause at this stage and then we'll come back to this in the next section. Cheers. And we'll just stop that end meeting. There we go.